Yeah, well, hello, and this will be the last actual lecture, formal lecture as such, for at least from me anyway. So we're going to look at three-phase transformers. So, well, three-phase transformers is basically where we have all the three phases, or transformers all the three phases, on one single core. So this is a picture that depicts what we mean by a three-phase transformer. So I mean, we could have one transformer for every phase, and that does have some advantages because we only need to replace one transformer when there's a fault. But the advantage of using three-phase transformers is that because we're using a common core, they're smaller and cheaper. So we can have four configurations of transformer connections: delta delta, star star, delta star, and star delta. So we're going to look briefly, really, at all four of these. Before we do that, we're going to look at some definitions. So if you consider we've got three transformers over here, one, if you like, for each phase, and there's something called the bank ratio. So we have the line voltage and we have the phase voltage. So the bank ratio is the primary line voltage divided by the secondary line voltage. So here, for example, VLP is our primary line voltage, VLS is our secondary line voltage, and VLP over VLS. And the other definition is the phase ratio, which is the primary phase voltage divided by the secondary phase voltage. So this is also equal to the turns ratio. So these are two useful definitions. And as we'll see, the bank ratio and phase ratio are equal when we have delta delta or star star connections. So we can look first at delta delta connections. So we can join them up in this way. So effectively, if you go down here, we see they're in series, and then this goes back to the red phase. So this is effectively a depiction of this configuration. Okay, so we're going down here, along here, up here. And what we see is there's no phase shift between the primary and secondary line voltages. So you can draw a phasor diagram, and of course these voltages will depend on the turns ratio, but the line voltages for each one are going to be the same. For each, for primary and secondary, are going to be the same. And the bank ratio then would equal the phase ratio. So we can have a star-star configuration. So you see each of these are connected to the star point in the secondary and the primary. And what we see is there's no phase shift between the primary and secondary line voltages. And again, the bank ratio and the phase ratio are then equal. So by delta star we mean that the primary is connected in a delta configuration. So we get this phasor diagram, and the secondary is connected in a star configuration. And what we find then is the secondary line voltage will lead the primary line voltage by 30 degrees. So this is the line voltage for the red-yellow phase, red-yellow line, and that leads the primary voltage red-yellow by 30 degrees. This angle here is 30 degrees. Okay. And because we have this configuration, so in other words the phase voltage is square root of 3 of the line voltage for a star configuration, and the bank ratio is going to be the phase ratio divided by square root of 3. And we can swap those around. And then we see that the secondary voltage is not in phase of the primary, the first degree phase shift. And we see that the primary voltage is 1 over square root 3 times the line voltage. So the opposite basically to the delta star configuration. So that's all well and good, but what about some applications? And so the first thing we want to look at here is, in terms of applications of the three-phase transformer, is insulation voltage limit. So what we want to do is want to get the voltage across the primary and secondary windings as low as possible to minimize insulation requirements. So this becomes a bigger issue on a high voltage side of the transformer. Okay, so you've got to remember we've got insulation around these wires, and you want to get the voltage across that insulation as low as possible. So what we want is advantageous to have only the phase voltage, because that's the where the phase voltage is the line voltage divided by square root of 3 across the windings on the high tension side. So if we step up, we want a Y configuration on the high tension side. So by high tension I mean where we have the higher voltage. So you see we have delta Y configuration. Why is that? Because we're dividing the line voltage by square root of 3, so the phase voltage will be reduced on the Y side, on the high tension side. And similarly, when we're stepping down from a transmission line at a substation to a lower voltage, then we would want the Y connection on the primary side. Okay, so you've got to imagine we've got some transformer, we've got a transmission line, and we've got another transformer, and on the transmission line we want high voltage, so it's just a high tension transmission line, because we want as small a current as possible going through that transmission line. Okay, so when we're stepping up here, so it's a step up transformer from our power station over here somewhere, we want a delta Y connection, and when we step down on this side we want a star delta connection. We want the Y part of the transformer on the high tension side of the system. So the other application of three-phase transformers might be a grounded secondary. So this is for safety reasons, and we might want to have a grounded neutral point on the secondary windings. So if we want a, so for example, if we've got load equipment here, and that load equipment is grounded, we may want to connect that ground to our neutral point of our star configuration. So if that's the case, we'll either want a YY, a star-star configuration, or a delta-star configuration of transformer. Okay, so these are for safety reasons, so that the load equipment is at the same potential as our neutral point of our transformer. And sometimes we might have a a fault. One of our transformers doesn't work. So there's something called an open delta configuration. So we've got a single three-phase transformer and we connect it as a delta-delta. And one of these transformers becomes defective and has to be removed. We can feed the three-phase load on a temporary basis with the two remaining transformers. So this is a main advantage of the delta-delta configuration. So there is a note here that when we operate in this open delta configuration, then the transformers are derated to 57.7% of their normal rating. So for example, if we got three transformers with 50 kVA rating, then the maximum rating there would be 150, and 57.7% of 150 would be 86.7. So the maximum three-phase load must not exceed 57.7% of 3 times 50 kVA. So that's an advantage and application of a delta-delta configuration. So a quick example here, just to finish off. We have three-phase transformers required to convert a 1 megawatt wind turbine generator to grid voltages. So we want to calculate the bank ratio and phase ratio for 690 volt to 330 kilovolt delta Y connected transformer. So the bank ratio is the voltage line primary, which is 690, over voltage line secondary 33,000, which is 0.021. Because this is not delta delta or star star, then the bank ratio would not equal the phase ratio. So the phase voltage on the primary is going to be 690. Because the secondary is star connected, you have to divide 33,000 by square root 3, and you do that calculation, you end up with a phase ratio of 0.036. Okay, that completes this final lecture from me. Please, if you have any questions, problems, again, please ask me. And we should do some examples next. I'll try and do them live in the lecture and see how that goes. Mainly because I'd quite like doing lectures live, and I haven't had a chance yet. So we're going to try that out on Zoom. I think it's time. It should be time for your break. I hope it's time for your break now, or close to it. And then we'll spend the last hour looking at some examples. The examples I look at would come from the previous PowerPoints, perhaps the previous lecture PowerPoints. And next week we'll look at some examples on three-phase, and also maybe some more transformer examples. Okay, thank you very much for your attention.